Hello, wonderful people. So here we are. We will be starting chapter 7, but I thought we'd do a bit of review and go back and hit the highlights from chapters 5 and 6. So you might recognize this. This is chapter 5, Newton's second law of motion, and this is the review that we did at the very end of that chapter. So we'll just zip through this and bring back some fond memories. Here we go. So if you drop a book and a sheet of paper to show the different falling rates, obviously the book falls fast and the paper falls slow. Then crumple up a piece of paper into a ball, and now show that it and the book accelerate almost equally when dropped. So here we go. Did you see that? They fall at the same time. Now, I want you to imagine that you're holding the 1 kilogram book up over your head and a piece of chalk over your head. Now, which will hit the ground first if you release them at the same time? You should know this answer. Yes, the same. Now, I want you to imagine to come up with an argument about what you could say that would explain why somebody might say that the book falls faster than the chalk. If somebody was going to have the wrong answer, how might they justify it? That's good. And there's the answer in pink. So the book has more mass, so it is pulled harder by gravity than the chalk. So therefore, if the book is pulled harder, it's going to fall faster. Does that work for you? Now, switch it around. What's a good argument for arguing that the chalk would fall faster? Okay, so let's see. The book has more mass, so the book has more inertia. So when gravity starts to pull on the book is slow to respond. But the chalk being so light, once it's pulled, the chalk falls nice and fast. How do you like that? Now, these two arguments are coming from this relationship. The first one, where you say the heavy book will fall faster, you're saying that the acceleration, little a, and the force of gravity are proportional. So since the book has a bigger force, you're going to have a bigger acceleration. And the second argument is the opposite. So, I'm sorry, is from the second, not equation, because it doesn't have an equal sign, from the second proportionality. And that is saying that since the acceleration is proportional to 1 over the mass, then the chalk with the smaller mass is going to accelerate more quickly. Now, both these proportionalities are true. And where do they come from? They come from this equation. Acceleration equals force divided by mass. Now, the way that we usually write this equation is F equals ma. But I find that acceleration as force divided by mass makes more sense because of those examples. It just, where does acceleration come from? It comes from a force of gravity, and that force, the acceleration is the force divided by the mass. So now if we drop the 1 kilogram book and the chalk together, they both fall at the same speed, just like Galileo showed when he dropped a big rock and a small rock off the Leaning Tower of Pisa, 400 years ago, ballpark. So that's rewriting Newton's second law. And then the cannonball and stone, the big cannonball, the little stone, the acceleration is the same. There's a big force pulling the big block, but it has a big mass. So the accelerations are the same in both cases. Let's take a pause there. I'm not going to read this comic, but if you want to read it, hit pause and go ahead through it. It's just illustrating the example that we just did. The air resistance that a falling body encounters depends on two things. One, how big it is, and two, how fast it is going. Air resistance depends on both size and speed. As an object falls faster and faster, there may be a point where the force of air resistance is equal to the weight of the falling body. When the force of air resistance on the falling object is equal to the object's weight, what will the net force be on the object? 0. So if there's 0 net force, because the force pulling it down, gravity, is the same as the force pulling it up, air resistance. So if there's 0 force, what's the acceleration? 0. Does this mean that the object comes to an abrupt halt, that it stops? 0 acceleration means 0 velocity? No. 0 acceleration does not mean 0 velocity. It means that there's 0 change in velocity. So velocity is not changing when there's no acceleration. Why? Because of force equals mass times acceleration. If the force is 0, then the acceleration is 0. Now, I've made this slide years ago, and I find it just hilarious that May the 4th be with you is being recorded into this video on May the 4th. Ha ha ha. I'll post this too. Objectives, some things to consider. A problem. Let's go through this real quick. Okay, a pilot announces that the plane is flying at a constant speed of 900 kilometers an hour, and the thrust of the engines is a constant 80,000 newtons. What is the acceleration of the airplane? Well, if the plane is flying at a constant speed, the acceleration is 0, because velocity is constant. If anybody wants to say that maybe the aircraft was turning, you get an A+. So what is the combined force of air resistance that acts on the plane's outside surface and the engine pushing it forward? The combined force is 0. There's 80,000 newtons pushing the plane forward. There's 80,000 newtons of air resistance pushing it backward. And if the resistance were less, the plane would speed up. If the resistance were higher, the plane would slow down. Does that make sense? Draw a free body diagram, and we're done.